Enthalpy is simply the amount of energy or heat stored within a substance. And it's a vast and large number. It's usually the potential energy in something. We symbolize it with the letter H. However, we're usually interested in only the change in this because it's usually a large thing. So we are talking about delta H in this case. Also, enthalpy is a state function, meaning it doesn't matter how you got there, only that you end up getting to a certain place. At constant pressure, enthalpy, or delta H, is going to equal Q, or heat. It's going to be the same value, which is great for us because most of our experiments happen at a constant pressure of 1 atmosphere. It can be calculated several different ways, so let's start with stoichiometry. Stoichiometrically, if A and B come together to form AB, they're going to release heat. This would be an exothermic process. They are producing heat. Heat is a product. So 1 mole of A plus 1 mole of B makes 1 mole of AB and 1 kilojoule per mole. If I had 6 moles of A and 6 moles of B, I would produce 6 kilojoules. If energy were a reactant, that means we would have an endothermic process. We're adding energy. So if AB decomposes to AB after the addition of 1 kilojoule, that would be an endothermic process. So let's do a problem with one of these. Sample problem A in your packet is when potassium hydroxide is dissolved into water. It releases 43 kilojoules of energy. We're asked to figure out a couple things based on this. Since the energy, kilojoules, is being released, that means that 43 kilojoules, that temperature, is going to be sent into the surroundings. So the beaker would feel as though it was going to get warmer. And since energy is being produced, that means that we are losing that energy. Energy is exiting the system. This is an exothermic process. Lastly, we're asked to calculate how many kilojoules would be produced by 14 grams of potassium hydroxide being released. Well, we can't do anything in grams, so we're going to have to convert that grams into moles. So 14 grams of potassium hydroxide become how many moles of potassium hydroxide? We end up finding out, we divide by 56, and we end up with 0.25 moles of potassium hydroxide. If we now convert that using the mole-to-mole ratio of potassium hydroxide to the enthalpy, 43 kilojoules, we can multiply 43 times 0.25, and we find that 10.75 kilojoules of energy are produced. Another way to calculate enthalpy is what we call calorimetry. And you can do this using two different methods. Or two different devices. The first is the is a styrofoam calorimetry, or a styrofoam calorimeter. It simply is a styrofoam coffee cup with a beaker inside of it. The styrofoam prevents the surroundings from absorbing any energy from the system, and all of the energy is instead transferred to a thermometer, which then will absorb it all, and we can just simply note the increase in temperature. The increase in temperature, or the increase in heat, or decrease in heat in some cases, can be related to delta H because we know what the conditions are. We know that they are standard conditions, and since we know mass and volume, which will become important later, we can do a lot of different calculations based off of this. The other method or other device that we use when we do calorimetry is the caloric bomb. A caloric bomb is simply a crucible in which a sample is placed and a wire is put through the sample. As energy or as electricity is passed through the wire, it ignites or combusts the sample, and that releases a large amount of energy or heat. That heat is picked up by what's surrounding that bomb, which is typically water. And since water increases its temperature at a very set rate, which we'll talk about next, we can measure the increase in temperature of the surroundings and determine how much energy was stored within our sample. The calorific bomb is often referred to as the constant volume because the volume stays constant in this case. Now there's some vocabulary you'll need to know for this next section to make any sense, so let's start with heat capacity. Heat capacity is simply the amount of energy it requires to raise the temperature of a sample by 1 degree Celsius, and its units are joules per gram or per Celsius. If we're talking about a very specific substance, we're talking about its specific heat. It's the amount of energy necessary to raise 1 gram of a particular substance by 1 degree Celsius. And therefore, its units would be joules per gram degree Celsius. And this is a constant that that is usually given to you, or you are solving for. A variation, it can be solved by dividing the quantities by grams of material and multiplying by the degrees Celsius changed. A variation on specific heat is molar heat capacity. It's simply the amount of energy needed to raise 1 mole. So it simply changes our units from grams degrees Celsius to moles degrees Celsius. These values are usually given to us. For example, the specific heat of water is a given value of 4.184 joules per gram degree Celsius, which is exceptionally high given water's very low molar mass and other chemical components. However, because it has such a high specific heat, it's what makes life on Earth possible, because it stays cool for a longer amount of time. It takes a lot of energy to heat up a gram of water. 4 joules is a pretty substantial amount of energy. And since we know the specific heat of water, if the temperature of the water around our bomb increases by any amount, we can calculate how much energy was released given its specific heat if we knew the gram amounts of water that was present. Lastly, in order for us to move on, this needs to be a little discussion on some units. Units are our friends, and it's actually units that would, if you're totally lost, look at the units that you're given and look at what you're trying to get to. For example, if I'm given grams in degrees Celsius and I'm trying to find heat, I know that I can multiply this by grams and degrees Celsius, and I should be able to come out with a unit for energy, with joules in it. So the first unit is a non-SI unit, the calorie. A calorie is simply the amount of heat necessary to raise 1 gram of water 1 degree Celsius. And since we know the specific heat of water is 4.184 joules per gram degree Celsius, if we're raising the temperature of 1 gram of water 1 degree Celsius to make a calorie, we therefore know that 1 calorie equals 4.18 joules per 4.18 joules. Another unit that gets tossed around a lot is kilocalorie. And you see this at the grocery market when you're looking at your, if you're counting calories. A kilocalorie, the calories you see on the side of your boxes, you'll notice they're all in capital C. That's because it is a kilocalorie. This is a shorthand that was developed. That's why this is a non-SI unit. So if you're on a 2,000 calorie diet, you're actually on a 200,000 calorie diet. Energy can be calculated using a formula, an old friend of ours from general chemistry or from pre-AP chemistry. Q equals mc delta T, where m is the mass. Actually, let's start at the front. Q is energy, so that's going to be in joules or calories. M is the mass, which is going to obviously be in grams. C is the specific heat of whatever substance it is you're talking about, and that has its units as joules per gram degree Celsius or calories per gram degree Celsius. And lastly, delta T is the change in temperature. So T final minus T initial. And all of this comes with the understanding that it has to be at constant pressure. Since we're at constant pressure, that means Q also equals delta H. So this formula could be rewritten as delta H equals mc delta T. So let's do one of the problems that uses this. Sample B in your packet. First, let's start off by highlighting everything we're given and what we're asked to solve. We're given the volume and molarity of two solutions that end up getting mixed together, originally at some certain temperature, and then it's raised to a higher temperature. We're told that they have a set density and a specific heat, and we're asked to calculate the change in enthalpy, or delta H. So we know we're going to be solving for delta H. And the only formula we know so far for delta H is Q equals mc delta T. We're given a C, we've got a specific heat. We're given two different temperatures, so we've got a delta T. Where things get a little shaky is that we aren't given any mass here. But if you look, we're given a molarity, and that's moles per liter. So we can take those and convert them back into grams if we knew that they had a set density. And sure enough, they told us it has a density of 1 gram per centimeter cubed. A centimeter cubed is the same as a milliliter, so this would be 1 gram per milliliter. So whatever we get for the grams in solution, we can also assume it's a 1-to-1 ratio of the density, and so we can go from milliliters to grams. So let's go and figure out how many moles of each reagent we had. So we find that we have 0.1 moles of each reagent. We need to convert those back into grams because remember the formula is Q equals mc delta T. So we need a mass. So we need to convert them back to grams. So from moles we can go to grams by multiplying by the molar mass of each compound. Once we do that, we'll be able to figure out how many grams we had in the overall sample. So we had 4 grams of sodium hydroxide, 3.65 grams of hydrochloric acid. Together, they made up a total mass of 7.65 grams for the entire reaction. So now we can take that and plug it into our formula. In place of m, we put 7.65. We're given a specific heat, so we're going to plug that in. And we're given two different temperatures, so we can plug that in for delta T. And we end up with this, so we're going to multiply all that out. And if we look, our units actually cancel here. Grams cancels grams. Degrees Celsius will cancel degrees Celsius. We'll be left with joules. Delta H is energy. It has to be in joules, so that makes sense. Multiplying all this out, we find out that we produced 214.5 joules.